Yeah. All right, folks. It's a Dijkstra's warm-up if you haven't already started on it. So we'll go through an example. I'm pretty sure this is on your exercise 5. There is a Slido open. Also, apparently, the audio didn't capture from Friday's lecture, and I have absolutely no idea why. I feel like this is how loud I usually sound. The mic is clearly picking me up. Okay, we're going to keep an eye on it. Sorry, internet viewers. I don't know what happened. Computers are mysterious things, y'all. All right, go ahead and practice Dijkstra's. Fill in the Slido, and we'll come back together to discuss it in, let's say, 2 minutes. Go ahead. All right, how's it looking? I'm actually smart enough to have put this in a separate tab today. Oh, we've got 91 answers. Should we see how we're doing? Show results. So I was asking you what the final distance to vertex F is. Aha, 4, wow. Lots of consensus today. That's nice. It's the sun, huh? Okay, let's go through it and see what we end up with. So we're going to start at A, which means we have 2 outgoing edges, the one going to the C and the one going to the D. Which one are we going to pick? Are we going to C or D? D. Yes. So if I click, you can see here's our sort of first step. We mark A as known, and like we're going to represent it in red as we've been exposed to these edges, but we haven't locked in those edges yet. So there's like sort of 2 phases when we first encounter a new vertex. There's us looking down the road and deciding, are we going to travel down there? And when we look down the road, right now we have what we would sort of call preliminary distances for C and D. We're going to pick D because that's the smallest one. We're going to be greedy with this algorithm. We're going to pick the best choice at every stage. And so we're going to pick D. Now that we're at D, we look and we see D has 4 outgoing edges. 1 to B, 1 to E, 1 to G, and 1 to F. And so that actually now exposes to us a way to get to each of these vertices. But again, we're going to do the greedy algorithm thing. Which vertex are we going to mark as visited next? We went A, D, what comes next? We're going to pick the one that's got the shortest distance. Which one's that? E, yes. So we're going to pick E. So we sort of lock in E. And you can see, too, we're updating our, did we do that? What did it do? C. Oh, sorry. C and E both have 2. So both relevant. And in that case, we could theoretically have, like, both are correct. We were going to split ties here based on alphabetical order. So we'll just pick C for goodness. But both have a distance of 2. We lock it in. We mark its back pointer. Now we have the remaining ones. And you can see, too, as we're doing these things, I think it was in the last one, right? The very first time we were exposed to F, we would have gotten there by traveling along the 1 from A to D, and then along the 6 from D to F, which gave us that original distance of 7 to the F. But once we sort of lock in that C, and now we look at the outgoing edges from C, that's the first time we're exposed to that 2 that goes from C to F, which is how we updated, see how it's red now? Instead of being a distance of 7, we found a new shorter distance to F that is 4. So Dijkstra's will update the distances. That's, remember that little if check inside of the for loop, inside of the while loop, that's like, hey, if new distance is shorter than old distance, that works to go from infinity down to the first time we saw it, but it also works in this way, where if we encounter a shorter path to that vertex as we go along, we will update it. Okay, now that we've processed C, what comes next? Oh, sorry, was there a question? Yes, please. If the edge from A to C was actually a 3, what was the second part of the question? Oh, no, because then the distance to C probably would have been 3 instead of 2, right? It is just based on where's the next closest vertex. Exactly. So it's this greedy algorithm. We're just picking who's the next closest out of the possible routes I have available to me at each step. Yes? So if we go back, sorry, it was me, I was looking at it. So right here at this step, we've gone A and we've gone to D. And then we're looking at all of the other possible places we could go. We could go to B for 6. We could go to C for 2. We could go to E for 2. So those two are equivalently of 2 distance, or a 7 or a 6. And we're going to pick the shortest distance, which is 2. We have 2 options. And apparently past KC chose to go to C first because it does make sense to go to the alphabetically first one. That's not actually a part of Dijkstra's. That's just whenever I give you an exam to give you a deterministic route, I usually say break ties by going to the smaller vertex or the alphabetically first vertex. But if there weren't 2 with the exact same distance of 2, let's say to our friend's question, that distance to C was actually 3 instead of 2, we would have gone to E first because it was 2 and that would have been smaller. So the only reason we did C instead of E is just because we broke a tie. But you technically, according to the Dijkstra's algorithm, technically either would have been within the algorithm. Totally relevant. Yes. Yes? Yes, yeah. So this is interesting in that we're sort of exploring possible routes by crawling, but I'm going to constantly keep going back into this list. Now, if you're asking yourself, how do I implement that? How do I know which vertex has the shortest distance? Do you remember on Friday we talked about this magical structure that would keep all of the possible next vertices sorted in minimum order, and that would pop out for us if we removed them in the next closest vertex? Anyone know what I'm getting at? I heard it. Yes, please help us. The priority queue heap, yes. So this decision that I'm doing manually here, where I'm like, where do I go next? To the next closest vertex. The priority queue min heap is what you will be using in your code to just remove min, just be like, who's next? Who's not the next shortest distance that I'm going to travel? And then you loop. So we removed min, and it said, go to C. We're like, okay, great. Now let's look at the edges coming off of C, do any updates. Now when I call remove min off of my min priority queue, which vertex is it going to give me? Yes, E. There we go. So we lock in E. Now we have 3 options left, B, F, or G. Where are we going to go? B it is, because it's the smallest. Love it. We've locked it in. We've got 2 options left, F or G. Where are we going to go? F, I love it. And then where? G, amazing. So that's our sort of final mapping. So once we've finished running Dijkstra's, what we have at the end result is we have those 2 maps. Remember on Friday where we had BFS, but in order to change it to shortest path BFS, we just added 2 maps that we kind of filled up along the way. We've carried that forward in our Dijkstra's. So right now, this table essentially represents like your final artifact, the goal of running Dijkstra's. And so right now, I have 2 maps, hash maps for performance, yep. I've got 2 hash maps filled up. One that's probably called dist2, and then one that's called like edge from, or you might call it back pointers. And so now, at this moment in time, if I asked you what is the shortest path from A to F, I would look at my little table here and I would call into the hash map. I'd be like, hey, what's the distance of F? And it would spit back out that 4. And I'd be like, oh, great, good to know. How do I actually travel to accomplish that? And then what I would do is I would build the path working backwards according to the back pointers. So I would see F's back pointer is C. Great. C comes right before F in this shortest path, and then I would jump up to C and I'd be like, C, who's your back pointer? A. Oh, okay. That's how I would reconstruct the path that the shortest distance from A to F goes A, C, F. I reconstructed that by going through the back pointers. That part tends to trip a lot of people up when they're implementing. They sort of forget that thing. They're like, how do I actually get the path out? And we're going to construct the path by sort of looping over from back pointer to back pointer until I get back to the source target. So I start with the thing where I'm trying to head. Like let's say I want to go to G. I would see G's back pointer is D. Great. And then I would go to D's back pointer. That's A. So I know the shortest path from A to G is ADG. Any questions? This is like the last I'm going to talk about Dijkstra's. So I just want to make sure that we answer all the questions so far. Cool. Okay. Amazing. Don't worry. You can ask lots of questions when you're programming it. I know it'll happen. Yes? Do we need to rerun the entire algorithm for a different start node? That's an interesting question. What's our intuition? What do we think? Yeah, because it is all kind of in relation to the start vertex. But here's the flip side of that question. If I asked you for the shortest distance from A to G, and you ran Dijkstra's, do you have to rerun Dijkstra's to give me the shortest distance from A to, say, D, or something different? No. Technically, what I have done by running Dijkstra's all the way until its very end is that I have found the shortest distance from my source to all other vertices. Now remember, there is an optimization. Because it's a greedy algorithm, The moment we lock in the distance to a vertex, we're good. So if we encounter our actual target vertex and we haven't finished running Dijkstras, we can just bail out. We can break, we can return. We can be like, oh, I don't need to keep iterating because I have found my target vertex. I've encountered it, which you will probably want to do for performance reasons on your homework. Cool. Okay, great questions. All right. Wonderful. Okay, announcements. Okay, so I clearly didn't finish the slide, but I put the one most important announcement on here. So a reminder that your midterm resubmission is due on Wednesday. We have to grade these things again. It's very hard to take late exceptions and do manual grading, so please, please, it must be turned in by Wednesday. It is Monday. If you, for some reason, are in a situation where you cannot turn this thing in by Wednesday, send us an email ASAP. I have this whole plethora of things I can do to help you if you email me before a deadline, but after a deadline is a different conversation. Okay? So, please, no lates. No late days can be used on this. Please let me know if you are in struggles. I'm hoping that a week to do what I was hoping was like an hour or two of work was fair. Okay? Cool. We will reopen. So what we're going to do is we're going to take your resubmission. We're going to grade it. We're going to release the grades for that, and we will open the regrade requests for the original midterm. So if you, in doing all of your analysis, found that maybe you got unfairly docked points or something like that, we can talk about that when we release all of those grades. Just so you know, when we say regrade, that is different from a resubmission. A resubmission is what we're doing with the midterm right now, which is like, take another shot. Tell us what you would have answered. That's what we want to know. A regrade request is, hey, TAs, I think the rubric was incorrectly applied. We've been getting a lot of regrade requests to the exercises that are like, oh, darn, I got it wrong. Here's what I would have answered. And while that's really nice, we're all like, yay, good for you. It's like the regrades, I can't do anything with that kind of information. So just keep in mind, difference, regrade, you want somebody to reevaluate the rubric and how it was applied. Resubmission, that's what we're doing for the midterm. You can like actually write new answers, and we're going to give you credit for the new answers. Also, I should have written on here, P3 is due Wednesday, right? Yes. Had wonderful conversations in office hours last week. I get the sense that things are progressing all right for P3. I know that P2 just startles everybody into starting earlier, and then P3 feels so kind. But exercise 5 is out for 2 weeks. We didn't want to give you too many due dates, so exercise 5 will be due a week from today. Any course administrative questions at this time? Yes?
During office hours, can you ask questions about the midterm resubmission?
Ooh, okay. During office hours, can you ask questions about the midterm resubmission? You can ask conceptual questions, and the TAs may give you conceptual answers, but if you're asking about like how your midterm was graded, we ask that you take those questions to Ed, because that way we're going to route you to the right TA that graded your thing, and that helps us keep everything really fair and consistent. Yes? Yeah?
Yeah, I asked a question about midterms with TA back. They said that they can't pre-grade the resubmission.
Yeah.
So how should I ask questions about it?
So you can ask conceptual questions like, hey, I'm trying to understand tries. Like, let's walk through a different problem. But yes, generally, no TA at any point in this course can pre-grade your assignment for you. So, like if you're like, hey, look at my thing, did I get full credit? A TA will probably never answer that question, or should never answer that question at my behest, as you can imagine. But you can certainly be like, hey, I was looking at this other problem, or hey, I'm trying to understand this runtime, or this was an example from lecture, or I'm just trying to get like how AVL trees work. Those kinds of conceptual questions, totally valid. But look at my answer and grade it, or look at my answer and tell me what I will get is unfortunately not the kind of question we can have TAs answer. Cool. Oh my gosh, is that true? Wow, that's amazing. That's a miracle. Okay. Ooh, how would updating the DIS2 look in code? That's a really good question. So taking it back to Dijkstra's implementation, DIS2 is probably a map where the key is the vertex and the value is the distance. So when you find a new distance that is smaller than the distance already contained in the map, remember with dist 2, you're going to loop over and you're going to fill up dist 2 with all those infinities to start with. So by the time you're looping through all of your vertices, dist 2 should have an entry for every one of your vertices already. So at every new vertex, you pull out the current distance associated with that vertex. The first time you do it, it'll be an infinity, or max integer, which is equivalent. If the new distance is shorter, then all you need to do is just put the new distance back into that map with the same vertex. So like, let's say we had a vertex F, and it originally had a distance of 7. Then when you're ready to update it, you just dist2.put F and then 4 with the new distance, and it'll override that. Yes, question? Sure. Yeah, it's however you want to implement that. Yes. This is me being annoying and cagey right now, but I will say that is officially a design decision. So I can see where you're coming from, and I think that is a correct way of thinking about your design. That was a really annoying way to answer that. But yeah, technically it's up to you and your design, and so all you need is that you need conceptually to start with this sort of idea of like infinity distance away, so that the first time you encounter it, that will be the newest entry of. So however you make that work, totally for you. Because technically that run of V doesn't contribute to the complexity class of Dijkstra's anyway. So, do the directions of the arrows on the edges in these graphs matter? Yes, that's a really good question. So remember that the edges matter. You can only travel from like end of arrow to front of arrow. So at each time when I'm like working on processing a new vertex, I only look at the out edges. Like I'm standing at the source and I ask, where are the out edges going from? Where can I go starting here? The in edges don't really mean anything to me in that context. So I'm looking at the out edges, and in the pseudocode, that's that for loop. That's like for every outgoing edge from the thing I'm currently looking on. That's what they're looking at there. Why does Dijkstra's work? Like, what's the actual logic? So really, like, what this is literally a greedy algorithm is just we're making the shortest distance possible work at every single stage. And because we're sort of always picking the next closest vertex, then at the moment I lock in the vertex, I'm guaranteed that I've only made the minimum distance choices at every point up to then. And so that's why the greedy algorithm works. It wouldn't work if later on something happened where my distance 2 would get updated, say like with a negative edge weight or something like that. But because Dijkstra's has this requirement, no negative edge weights, we can be guaranteed that as long as we pick the shortest path, by the time we lock something in, that will be the shortest path to that given item. Yes?
Going back to the previous question, on the slides, I saw that C was an arrow pointing from C to D. So why was that still a valid option?
It might just be in the slides. Let's see. So looking at this, it looks like C has outgoing edges to D and F. Was there an edge that mysteriously popped up? A is our source vertex, so we're always sort of asking ourselves how to get from A to anything else. Yeah? Okay. I'm sorry, I don't know if that fully answered. Yes?
So Dijkstra is not like a path following one. It doesn't like go to a node, check every possible solution from that node, and then if there's nothing else, go back. It's just it always checks from A going forward.
Yes.
Like what's the shortest path.
Yeah, so the algorithm is pick a start vertex, look at the outgoing edges, mark some possible distances, pick the shortest one, repeat. And so, for example, as we got in, right, like we weren't necessarily building this path like sequentially from A. We kind of did jump around to different vertices a little bit, but we're always in the context of like shortest distance from A is what we're always asking ourselves. But because of that amazing min priority queue heap, I'm not technically like just building the path by crawling it. I'm sort of building the path by storing this queue of vertices yet to visit based on how far away they are. I'm just pulling the next closest one off of the queue. Okay, cool. Okay, I think it's time for some new algorithms. Great. Okay, so that was all about pathfinding, shortest path. Now we are going to talk about minimum spanning trees. Let's start with a problem. This is a fun one because this is literally the problem for which these algorithms were invented. It is the 1920s. That's really when this was invented. Wow, were there electronic computers back then? No. Saha. A computer is to computer science as a telescope is to astronomy. There you go. Technically just a tool. Okay, so it's the 1920s. Your friend at the electric company needs to choose where to build wires to connect all of the cities to the brand spanking new electrical grid. And what we want is we know that the way an electric circuit works is that as long as you're connected to the circuit, you get access to electricity. So our goal is not necessarily this specific path from one vertex to the other, but rather how do we build connectivity across all of the different things that need to get added to the electrical grid. We know it's costly to build the wires and dig underground and do all that stuff, so we want to find the cheapest way to make sure that every city is somehow connected to the electrical plant. Like I said, this is really the problem that they had in the 1920s. That was generally when commercial electricity started to become available. I don't know how many of you are here in Craftsman Homes in Seattle, but I know that the apartment I'm in was certainly built before commercial electricity was available. You'll see it actually all over Seattle, very interestingly. And this was the problem they were trying to solve. So, enter the MST problem. What do we need? We need a set of edges such that every vertex touches at least one of the edges. This is described as a span of the graph. So what is the minimum summation? What is the minimum total edge weight count that would still maintain total connectivity across each vertex? Now, here's the thing. I don't care about the shortest distance between any two vertices. Like right now, if I wanted to walk a path from the electrical plant to D or something like that, I'd have a really long way to walk. Or from the electrical plant to E, I'd have a really long way to walk. I don't care. That's not what this is about. This is about maintaining the connectivity across all of them. Here's what I will also tell you. This set of edges, we are guaranteed will never have a cycle. And in fact, we are guaranteed that we are going to contain exactly v-1 edges. Do you remember when I brought this up in the shortest path problem with Bellman-Ford on Friday? That I like to think of this as a fence post problem, where the vertices are the posts and the edges are the fence between them. We have one more post than we have connecting fence between them. That's what's happening here. To get the minimum amount of connections, to keep this as one nice contiguous fence or whatever, we're going to have exactly v-1 edges. And with v-1 edges, I can't have a cycle. A cycle, remember, being a way to leave one vertex and come back around to it without recrossing an edge. If we have a cycle, well, then I have an unnecessary edge, and that is not the minimum spanning tree anymore. Questions about this definition? Okay. Is there always going to be a unique singular MST for a given graph? Take a minute, talk to those around you, and if you can, come up with an example where you wouldn't have a unique MST, if that helps. Go ahead, talk for a minute. All right. Do we have any interesting thoughts we'd like to share? Can anybody come up with a situation in which there might not be a unique MST? Anyone? Yeah.
We thought of a triangle where all the edges have weight 1.
Ah, interesting. Yes, a triangle, so you've got a cycle, and all of the edges have the weight of 1, meaning you have multiple edges with the same edge weight. So if that's the case, if you have a triangle, any 2 of those edges could be your MST. That is absolutely a scenario in which you could have non-deterministic MSTs, but they would still be valid. Yes?
I'm not sure if this counts, but if you take away the edge from A and add the edge from the factory.
If you take away this one, and sorry, what?
Add factory
To D? Yes, that's very possible. Yeah, that probably could be an MST. Yes, as long as those things are still connected. You need, essentially, when you get rid of this little line here, you have what I would call 2 connected components. You've got the factory to B, and then you've got the DACE component. And you need to find some way to transform those 2 separate components into 1 component. So you did it by adding an edge from D to the factory. You could do it from factoring C to the factory, from E to the factory, or from any of those to C too as well. Okay. The big key takeaway with the MSTs is if there are unique edge weights, you will have only 1 possible correct MST. But if you have duplicate edge weights, there might be multiple. It is all just based on edge weights. So this is just more details. Please, yes, note, this does not necessarily minimize the path from each vertex to every other vertex. I am hammering this in because there is a very common student misunderstanding here. A lot of people mix up MSTs with Dijkstras. Shortest path, I like to think of that as I am a physical delivery person. I am physically walking from one location to the other, and I want to walk the fewest amount of steps. The MST is the electrical grid. Everybody's got to be attached, but nobody's walking from any vertex to another vertex. It's about connectivity, not about a source and target. It's okay if you mix those up. A lot of people do. Okay, so we've got a bunch of things. You can read this stuff. This is mostly just thoughts for later, but we're going to start to talk about algorithms to find this MST. So we've learned about this thing called greedy algorithms, where we're going to make the sort of best choice possible at each stage. And I will tell you, there's actually 2 common, famous MST algorithms. We are going to talk about both of them. So, this is yes. Shortest path, minimum spanning tree, different things. Thank you, Past Casey. Here are 2 algorithms. Okay, so here are some intuitions. We could think about doing this vertex by vertex, where we sort of have a set of vertices that are representing the current MST as we're building it up, and have each vertex remember the cheapest edge that could connect it. So what is the cheapest edge connected to each vertex? Let's use that to connect it to the rest of the group. So we could kind of go vertex by vertex and be who's your cheapest incoming edge? That's the one we're going to use. So that's vertex by vertex thinking. Or we could go edge by edge thinking, where we would just take the whole list of edges and sort them and just be okay, what's the shortest edge? I don't care who it connects, but that's in the MST. And then the next shortest edge, does it connect 2 things that weren't previously connected? That's in the MST, and I just keep repeating that thinking. So one sort of goes edge or vertex by vertex and asks for its shortest edge connected to it. One goes all the edges, sort them, and then pay attention when you're selecting which edge in if it truly adds to the connectivity you're looking for. Great. That's exactly the 2 algorithms. One's called Prim's, one's called Kruskal's. They're named after dudes. Again. Please, somebody, let me say your name instead. Okay, great. So let's talk about Prim's algorithm. Prim's is the one that goes vertex by vertex. And so because it does that, like, these used to be these fabulous YouTube videos that they took down. Why would they do that? And no good YouTube videos I can find anymore exist. But these are visualizers. You can see what's happening in the gray is that's a little graph under there. And the black lines are sort of showing you which parts of the graph are processed as the algorithm's running. Look at Dijkstra's. It looks like when you run Dijkstra's, there's sort of this little nebulous moment here, and then a bunch of branching stuff off of that. That makes sense. Dijkstra's has a source, and then we start to explore from there, right? Prim's, this is just, it's all over the map. What's happening is jumping around because we're going vertex by vertex, looking at each of their individual edges until we eventually end with assortedness. So again, the distinction, we're not starting at a source vertex, we're looking at the graph as a whole, trying to figure out its connectivity. Somebody do a good visualizer, and I'll put that in here. Okay, so Prim's algorithm, how do we actually program this? So here on this slide, I have the pseudocode for the Dijkstra's algorithm, and you can see everything in black and blue is the Dijkstra's algorithm, and then I made one little change there. And this is actually how they got to Prim's algorithm. They just took Dijkstra's and further adapted it. I am not going to ask you to implement Prim's, but I think it is interesting. And again, a reminder that that sort of BFS is how we built Dijkstra's. It is still also how we build Prim's. But you can see what we just do here is that Dijkstra's checks for shortest paths. We don't care about shortest paths. We only care about the overall weight. So we only care about, like, could, like, this expand our connectivity while keeping the overall weight summation of weights down. Great. So here, let's actually walk through the algorithm and you'll see how it works. So here is our graph. We are going to put A in as our source, just we need somewhere to start, but we haven't really added anything. It's just sort of like, I'm thinking of this as having an overlay, and it's just got a single vertex kind of floating around. No edges have been added. Now I need to go through and figure out which edges I'm going to add to grow the connectivity until I get to that MST. So I look, and I see that I can get to B, C, and D from A. I am going to pick the shortest edge, 2. That's going to get me connectivity between A and B, so I'm going to pick it. Great. I'm going to look at the other possible options. Look at it. I jump down there to the next smallest distance, which is F. F has a connecting to B edge here, so I'm going to pick that. So now my MST is A, B, and F. I go again. I pick the 4. That's this edge here. 4 is the next smallest edge that will still include a new vertex that is not already included. So on and so forth. You can kind of click through these until we get there. And then I think, do I have a, okay, I really should have put an overlay of the final set of MSTs. But the final thing you want is the set of MSTs. Here you would see it with these edges. This set of edges represents the MST. That's your final sort of artifact at the end of it. Visually, and I will change this in the slides, is you could just think of it as like highlighting certain of the edges. That's your sort of final end state there. Okay. Okay. So you could see that we kind of like were asking ourselves, like Dijkstra style, we had a Dijkstra style table. We were asking like, oh, like what's the smallest edge off of this vertex? But your brain may have already kind of jumped ahead and just been like, yeah, well, the 4, like the 3 and the 2 was the smallest edge in the entire graph. So we started with that one. Great, it connected A and B. Then the 3 was the next smallest edge in the entire graph, and that added another one on. So like, why are we really looking vertex by vertex? It kind of feels like the edges are the ones that are driving the decision making in this particular algorithm. And so while the Prim's code was really nice and clean, I think for me as a human, my brain jumps to thinking in the edge by edge case. I find that to be more natural for my brain. So, Kruskal's, literally what you do, and here's the Kruskal's pseudocode, is you think of each vertex initially as its own little island, its own little disconnected island. And then we sort the edges. And we look at the very first, the shortest edge, and we ask, does it connect two islands that are not already connected? The answer is yes. You mark it, you include it in the MST, and then you look at the next edge. If for some reason that edge reconnects those two that you've just connected, you don't need it. Unnecessary. But if it adds in something new, it brings a new island into the archipelago or whatever, then you include it. So here, great. Here, it's maybe a little hard to see, sorry, because it's like light gray. But if you look at this set of edges, the smallest edge weight on the entire graph is this 1. So I'm going to include 1. I'm now marking this as my MST. So what I used to have 1, 2, 3, 4, 5, 6. I had 6 separate islands. By marking this, I have collapsed 2 islands together. So now I have an island A and C, and then 4 other sort of little independent islands. And I look for the next smallest edge. I see the next smallest edge is this 2 between B and F. So I select that one. Now, instead of 6 islands, I have 4. 4 islands. And then I go to the next smallest edge, which I can see there's a 3 here. And I ask myself, does the 3 connect 2 islands that were not previously connected? If I add this 3 in, is it going to expand the connectivity of one of the islands? Yeah, I agree. So we're going to include it. Great. Now I'm down to 3 islands. I'm going to keep repeating this until I get to one happy, all-connected island chain. So I look. My next edge is this 4. Do I want to include this 4 in my MST? Yes, it connects 2 islands that are previously not connected. Then I come down here, and if you can kind of see it, there's a 5 in here that will connect the C and D. Do I want to include the 5? I agree with the head shakers. No. C and D are already a part of the same island chain at this moment in time. That addition of 5 would not extend the connectivity. So I skip it. Then I go over here and I see there's a 6. Am I going to include this 6 in the MST? Aha, yes. And there we go. All of our islands are now connected. I just sorted the edges and went from smallest edge out. I skipped one of the edges. The intuition for this is that like the minimum spanning tree will likely include the edge weights of the smallest weights. And we just move through that. Any questions on the Kruskal's algorithm? Yes. This is still considered a greedy algorithm. The steps here are we're going to sort by edge weight, and we're just going to pick the smallest edge that extends connectivity at everything. So we sort of like, with that edge weight of 1, right away we're like, we're just assuming that's in. Greedy right away. Yes?
I know we haven't talked about runtime yet, but both of these algorithms seem like they would almost be like n squared.
Oh, because they're like exploring a bunch of things? Okay, you're right. We haven't talked about runtime because I have not even come close to talking about how you're going to implement Kruskal's. And in my past quarters, I made you implement Kruskal's, but I am just realizing I didn't check if it's in Seam Carver. We don't know either. Okay. When I made you do maze solvers, you had to implement this. And there's a bunch of fancy data structures that are secretly implemented only with arrays under the hood that we're going to talk about for the next 2 lectures that make it real efficient. So it turns out implementing Kruskal's by implementing the data structure of a disjoint set and then using that, actually kind of complicated, but it ends up with a pretty efficient runtime. With Prims, it's identical runtime to Dijkstra's. We're just using the Dijkstra's code. Yes? Ah, yes. Okay, so I think the key here is, see these 3 lines? And I like the word you use the word set. So what we did here is we sort of asked, like, hey, which set is at one end of this possible edge? What set is at another end of that possible edge? And then if those 2 are in different sets, then we've expanded connectivity, we add it. But this idea of knowing, like, are you in a set of sets? Are these 2 sets the same thing? That is a magical data structure you haven't met yet that we're going to meet on Wednesday. And then it will be very clear how to implement these lines. Let's see what comes next. Oh, look, there's even more practice. Okay, it's 4:19, so I'm going to let y'all do this on your own time. But come back on Wednesday where we are going to meet a brand new ADT and the data structure that is required to implement it. And we'll make this work great. All right, thanks so much, everyone.